Hello everyone, this is Kaylee Burdett with OCP. Welcome back to the hardware management track. We are going to go ahead and get started with our afternoon session. We have Alan Squina here with us, and he is going to be our first speaker. So I will go ahead and pass it over to him and let Alan get started. But before we do that, I just wanted to remind you that you can use the chat on the right-hand side of your Evan virtual platform to ask questions for Alan and any other speaker. And if you scroll down below the streaming window, you'll see the Etherpad, which you can use to ask questions or give your thoughts or comments on any of the topics. And we will go ahead and get started with Alan.
Thank you, Kaylee. Appreciate it. All right. Good afternoon, everyone. I am Alan Squina, and I head up business development for Asset Intertech's JTAG solutions, with a focus on our debug portfolio. Today, we're going to go review an innovative application for a mature technology, taking JTAG and embedding it as that capability as firmware within service processors, BMCs, and performing at-scale debug of the open compute project platforms. So I'll start off with a little bit of an introduction to the technology. What is it? Where did it come from? What are its applications, right? And then a little bit of a deep dive into the hardware access mechanisms, right? And that were introduced by OCP back in 2017, whereby we establish physical connectivity between the BMC, general purpose IO, and driving the platform CPU scan chains. We'll look at the architectural specifics, hardware, firmware, and then they spend a little time looking at the value, like why would one go about embedding JTAG right into a BMC? And it really revolves around the fact that you then have an embedded debug agent within the platforms. So essentially, debug at scale capabilities are brought to the table. Then we'll dive into a few of the many use cases, crash dump, some platform validation examples, and then application of JTAG for monitoring and telemetry services. And of course, this would never be, the presentation would not be complete without a discussion about security. JTAG is a very powerful technology, and with great power comes great security. So how do you protect and mitigate the platform? Once you add these additional capabilities to them. And then the calls to action. So what is JTAG after all? Very mature technology, actually created over 30 years ago, back in February of 1990, actually, and celebrated its anniversary. And it was created 30 years ago as a very elegant but simple solution. And back then, all of our engineering efforts were simple and elegant, right? We were looking at how to address the diminishing physical test access issue, right? That was happening as platforms became denser, more complex and higher speed. And those issues still exist today. It was codified by the IEEE as part of the 1149.1 specification. And since then, there have been numerous spin-outs, downstream standards, 1149.6, .7, 1687, 1500. And since it's been around 30 years now, you'll find JTAG just about everywhere. It's ubiquitous in most commercial silicon of any level of complexity. So it's out there in the billions and billions of devices that make up our electronic systems today. The technologies, the specifications, created a dedicated debug port, serial interface, 5 pins on each device. As you see in the diagram on the periphery of the device, the test data in, test data out, TDI, TDO, TMS, T-clock, and the optional T-reset signal. We also have a state machine, within each device, registers, walk its way through the JTAG state machine. And in yellow, at the periphery of the device, behind each pin, there is a boundary scan cell, which acts as a serial shift register. So we can shift data right around serially around the perimeter of device and then come out TDO. And also in parallel to and from the outside world, via the pins, and to and from, the internal system logic, right, of the chips. So handful of gates associated with each one of those yellow boxes, right? The boundary scan cells, a couple of hundred gates associated with the state machine and the tap controller, and that simple and elegant design has been acting for the last 30 years as an embedded engine, and a bunch of applications have grown up around it. And here are just 4 of them here in the main category. Test is probably the most well-known application of JTAG. Boundary scan test and JTAG-based functional tests are used in just about every electronic system factory, production facility in the world. Debug is what we're going to be talking about now. Also known as run control, and examples are the Intel in-target probe, the AMD HDT, and ARM has the core site debug and trace specification standard. Your validation, you use JTAG to access logic within the chip to perform hardware performance and conformance type validation or testing, and I'll give some examples of that in a bit. And then finally programming, since you can serially or in a parallel fashion shift data around and in and out those pins, right, the yellow boxes in the diagram, you certainly can program downstream components use JTAG, and that's quite a common use case or a common application. All enabled by that simple and technology, which is still around and still going strong. JTAG came to the attention of the OCP and working with the silicon vendors back in 2017, and Microsoft initially on the Project Olympus design, implemented physical connectivity between the BMC JTAG pins and the CPU debug ports. And the diagram on the right is an Intel design, but they had similar topologies for AMD and ARM as well. And what we see in the diagram is the BMC at the top right. At the time, an AST 2400. You have connectivity to some of the general purpose I/O off of the ASP device is connected into the XDP, the extended debug port, which in turn connects to the JTAG tap, right, and the sideband signals associated with the debug port, right, on these processors. Now, that hardware connectivity is optional. The implementation of providing the connectivity is now a de facto standard. So just about every design rolling out of the factory has this capability inherent in it. You can fuse it off, right, or jump it off, but the connectivity is part of the design spec. Various flavors of BMCs support the JTAG interface differently. Some support it in a software mode whereby you're just bit twiddling the interface, the scan chain, and you'll get a T clock or a test clock, sustained T clock frequency of 1 to 2 megahertz in that scenario. And some BMCs have actually implemented the JTAG mastering function, within a hardware, within RTL, and with which you're able to get a sustained T clock frequency, 12 megahertz, 60 megahertz, or even beyond, really just limited by the signal integrity of the implementation of JTAG signals on the design. So once that hardware connectivity is established, all you really need at that point is the JTAG driver, right, as well as some run control firmware, within the BMC to JTAG enable the platform. So let's look at that a little bit more detail. Service processors or BMCs, right? Certainly not limited to OCP platforms, but service processors of any type, A-Speed, Nuvoton, off the shelf, right? Implementations have been done with micro semi, smart fusion parts, right? Anything that can accommodate a fairly small footprint, 100K, 200K implementation to provide the JTAG driver and the run control firmware. Once that's in place, then there's a set of APIs that are available to initiate run control, those debug features, which are really reading and writing registers, I/O and memory. There's a optional remote host, back to that TCP/IP or other local or remote interface, green arrow at the left. That is certainly optional. With no remote host, that the BMC acts autonomously, the JTAG and run control API are available on the BMC, for the BMC to initiate itself. And the beauty of that is you get the debugging functionality without the exposure of the remote attack service and possibly a bad actor, getting into the system that way. If you're able to create a secure connection and you're confident in your BMC as a root of trust, you can implement the remote host connection. And then you've got the possibility of running some more sophisticated scripts or applications written in a higher level language like Python to support the Intel customer scripts, C scripts and such. The value of that is really debug at scale. We always think of JTAG as being deployed, locally. There's a workstation or PC on your benchtop, right? It's connected into some sort of hardware controller or pod over a USB or Ethernet, northbound connection. And then there's a little ribbon cable that interfaces to the debug port, the debug header that's down on the board itself, right? We take those arrows, right? We cross off the workstation, we cross off the controller, and we take that JTAG-based software and firmware and, deploy it within the service processor. So again, when you do that, then you don't have the requirement for that one-to-one, right? Those cables, right? External hardware, right? All of that goes away and you can do things at scale. And let's look at, these, some examples of functionality that, become useful in an at scale, context and are possibly less useful, right? When you've got the cables and the benchtop PC or workstation requirement.
So Alan?
Yes.
Do you have a question? Do you want to hold the questions to the end or take them as they come in?
Fire away, John. I think I can.
Okay. This is rather long question. So ARM cross-site infrastructure. Take the JTAG beyond tests, but it's on the comment discussion if you want to read it. Take the JTAG beyond tests, but also be used for software and hardware messaging. Other CPU architectures do so differently. Is there a plan to standardize the architecture so that software tools can be used cross-functionally across the CPU platforms?
Excellent question. You're actually stealing a little bit of my thunder, John, from the calls to action slide. so we could talk about that.
We can hold in the answer until then.
Yeah,
you can answer now or hold the answer until the end.
Let's hold the answer to the end.
Yeah, let's hold it. Yep.
Yeah, that way people don't leave my presentation before it's over. All right, very, very good question, though. Yeah, it's a very, very important issue, right? Deployment in heterogeneous fleets, for example, different suppliers on the CPU side, definitely. But the use cases, however, are common across all platforms. Crash dump is probably the one that gets the most attention, right? Especially given the fact that more often than not, a system hang or crash or wedge is an intermittent event. It's rare that you have the whole fleet going down, right? But one system might wedge once per week, right? And for one system, maybe that's not bad. When you've got a fleet of thousands and thousands of servers, right? You have to have some utilities, that operate at the bare metal level, right? To gain some forensics data, right? And use it to root cause, the source of the issue. Platforms crash or wedge, the platform OS is not available to run diagnostics in that scenario, of course, right? So you have to work out of band. And of course, the BMC is a very good candidate for autonomous crash dump type of applications. At the top, you see the table, right? In band is good, right? If the platform is still running. PECI is out of band, so definitely better than the in-band scenario. And JTAG, of course, is the most superior solution of the three, based on the fact that it can retrieve more data, and has more capabilities certainly than PECI. So in the case of a wedge, per the diagram at the bottom, the BMC fires up, initiates the JTAG API invocations, collects all of the data that is retrievable via JTAG, and either in real time or in a post-mortem fashion, uploads that into some sort of a system management environment that uses pattern matching, data correlation, AI-based systems, right, to merge that data, with other things that were happening in the platform at the same time. And it just gives you a tremendous level of insight, into root cause. At the other end of the spectrum is platform validation, right? The ability to read and write, just about everything within the system is intensely useful within a built-in test context, right? Utilities that are inherent within the platform and get invoked either during the boot process or any sort of an audit process, a regularly executed routine that happens at midnight, for example, could be invoked remotely via a diagnostic, that's invoked by a technical assistance center engineer, and hardware lab validation, right? There's a plethora of different applications of the platform validation scenario. One of which is stress testing of PCI Express link training. Most of the OEMs do regression and validation on PCI Express, right? The platforms are always turning. New add-in cards, HBAs are added into the platform. Firmware updates are done, within the upstream and downstream components. And you really want to optimize PCI Express performance, right? And one of the methodologies per the PCI SIG is to iteratively do a bunch of link retrains and speed changes, hundreds, thousands, 10,000 times, 100,000 times, and try to catch deficiencies, in either the link training and status state machine, variabilities in the margins, as part of the hardware design and layout. You want to avoid the surprise link down and system performance degradation, right? And so you want to catch this in the lab before you go live. So the benefits of this and using JTAG, with the embedded engine, of course, is you can run it on tens, hundreds, thousands of servers in parallel. It's fast because it's not depending on the operating system. It's out of band and at scale. All right, I'll continue quickly here. Monitoring and telemetry is dependent, is CPU silicon dependent, but in some instances, it is possible to use the out-of-band service management services module to collect data in the background with the platform running, without using JTAG to halt the platform. So you can collect, right, as part of logs, operational measurements, right? You can be collecting data on the real-time performance of the system in the background continuously with no performance impact to the platform, right? And then say there's a wedge. Then the BMC fires up the JTAG probe mode or run control API, halts the platform, collects the data. That's upstream to the data correlation system, and you just have more breadcrumbs usable to identify root cause. And last but not least is JTAG security. This is, of course, a very, very important topic because you're putting a very important, very powerful technology, right, in firmware, right, down on BMCs. And debuggability and security are two sides of the same coin, right? And there's always a balance between the two. The good news is there's been much research done, particularly in the defense industry, which uses JTAG selectively, all right, in some of their platforms, and with large scale systems, in IoT, for example, right, as evinced by the diagram at the top. We see some steps that have been taken, by some vendors. Mitigations happen at two levels, one at the chip level or the IC level, and that's accomplished either by fusing off TMS, right, and locking JTAG down entirely, or as expressed by the NXP document that's part of the references, down below that diagram at the top. NXP implements a number of secure JTAG modes, basically a challenge response mechanism, within the chip, right, that interfaces, via JTAG to the JTAG debugger over under the right, authentication, via a remote, key management system. So there's various ways to do this, and Intel, AMD, right, the various vendors have got they're all different implementations, right? And then at the board level, obviously the BMC needs to be at the root of trust, and some companies gone to the efforts of defining a trusted boot component device and routing the JTAG signaling through that device. And this was as part of the document number 2 down there in the references, right? And some further details on that, and the third reference by myself published at the AutoTestCon defense conference last year, which actually won best paper. But in any event, the TBC has firmware in it, right, to detect JTAG security events and then latch the JTAG if it detects something suspicious, until such time as the platform has been power cycled. That's one of many different implementations of having an external device monitoring and muxing JTAG. So to wrap up the calls to action, I think this addresses a little bit, hopefully, your question, John. We would like to contribute and work with the hardware fault management project, right? Is given the power of this technology, right? How do we deploy it universally, right? It will make a contribution to platform reliability, right? Being used particularly in defense for no trouble found, proactive maintenance, and it must be scalable across a heterogeneous fleet. Intel, AMD, ARM, RISC-V, whatever comes in the future. So what are the enablers? What are the key enablers, and what are the impediments? And then secondly, the security project. I think we all have a common interest to define a standard for secure silicon unlock, since all the vendors do things differently, and at the board level, right? How to mitigate, right, and protect against attacks on JTAG on the board, whether JTAG is embedded or not embedded. I think these are worthwhile topics to explore. And that's it for the presentation. Open discussion, please.
But John or Kaylee, can you guys see whether there are any questions? Okay, I see it here.
Yes, I just put one in the chat. If
Yep,
Alan and Hamel, you can read it.
Yep, let me read, Alan. There's a question from Pekan Gupta. JTAG was developed as a serial shift register protocol when other serial protocols were not mature or costly to implement in silicon. However, now USB controller being ubiquitous in most silicon, can USB replace JTAG? USB uses same number of pins and supports higher speeds than JTAG. That's the question.
That is a good question, actually. Replace, I would start by saying probably not. Some silicon suppliers have implemented essentially a USB to JTAG bridge. Intel DCI, for example, a direct connect interface is an example. So you access, you go into the platform, right, over USB. Right, and then the bridge itself converts to the JTAG logic, right? Which has been defined and been around, for years, and then translates between the two. So yeah, I mean, in that instance, for that sort of application, but that has primarily been constrained up to now as a benchtop implementation. I mean, today, if you want to get the power of JTAG, for example, via BMC, you have to go in over JTAG direct.
Okay, thanks for the answer. Any other questions, Kaylee or John, do you see?
I don't see any more coming in.
Okay, let's open the floor then. Any questions from the people on the Zoom meeting? All right. Thanks, Alan, for the presentation. It was good beginning of the afternoon session.
Thank you, Amal.